For this potentiometric titration, we need to gather some information before we can start calculating for our cell voltage. So we need to identify what is the anode and what is the cathode of our cell. The anode is attached to the negative side of a potentiometer, and we're told it's a saturated calomel electrode. So that has a potential of 0.241 volts. The positive side is the cathode, and here we have a silver wire and we have silver in solution. So the cathode is where reduction takes place. We have our silver ion and one electron, and that's going to reduce into silver metal. And the standard reduction potential of that equation is 0.799 volts. Now that is the standard reduction potential. We know from the Nernst equation that our actual potential is going to be dependent on the concentration. But the concentration of what? So now I'm going to do a quick general chemistry review. When we have sodium chloride in solution, what we have are the ions sodium and chloride. And when we have silver nitrate in solution, what we actually have are ions of silver and nitrate. And they're going to bounce around in that solution. And if anything can join together to form a solid, it will. Those are our solubility rules. And here we have the formation of silver chloride. So that is our insoluble salt. So silver chloride. Now silver chloride has a KSP value of 1.8 times 10 to the negative 10. So all of this information we need before we can even start to calculate. Now, we need to find the equivalence volume. So we're told we have a 25 milliliter sample of sodium chloride. And that sodium chloride solution has a concentration of 0.0500 moles per liter. Now, from our balanced chemical equation, which is right here, our titration equation, we know that 1 mole of chloride will react with 1 mole of silver. And the solution of silver nitrate that I have is 0.0250 moles per liter. Therefore, our equivalence volume is going to be 0.0500 liters of this silver nitrate solution, so 50 milliliters. So given these volumes, I have at equivalence, I have before, and I have after. We have different calculations we need to do for each of those scenarios. So let's start with our 10 milliliters of silver solution. And I know that this is 10 milliliters of the silver solution because of this right here, the volume of Ag+. That tells me that's the volume of silver that we have added. Now, I understand working with potentiometric titrations using a capital V can be a little confusing because that is the symbol for volts. But note the lowercase ag here and the use of milliliters here. That will tell you that it is volume that we're looking at. So what we have when we're going to calculate our E cell is this master equation, and it's going to be the E of the cell is going to be equal to the E of the cathode minus the E of the anode. I'm going to put that 50 milliliters up here so that I have room. Now, the E of the cathode is going to be dependent on the concentration of our silver ion, and it's dependent in using the Nernst equation. So 0.799 volts, which is our standard reduction potential, minus our constant 0.05916 divided by N. N here is 1 times the log log of our Q value. Now, our Q value is the concentration of the products divided by the concentration of the reactants. The products here are solid, and because they're solid, they have an activity of 1. So it's really the concentration of this silver we're looking at. So that is the E of my cathode, and then I need to subtract the E of my anode, 0.241. So I'm looking for that concentration of silver. Now, how many moles of chlorine have I started with? I have 0.0250 liters, and I'm going to multiply that by the concentration. So I start with 0.00125 moles of the chloride. And with the silver, I now have 10 milliliters of a 0.0250 mole per liter solution. So I have added 0.12325 moles of silver. Now, because when we add our ions together, our silver and our chloride, we make this solid, then the concentration of my silver in this case is going to be dependent on the silver that comes back into solution after I've made that solid. So I need to be looking at AgCl reacts to form some amount, well, we are in an equilibrium, plus chloride. So I've used up all of this silver. How much chloride do I have in excess? So I subtract these two values, and I find that there is 0.00100 moles of chloride in excess, and now I need to divide by the total volume. In liters, we have added 10. We started with 25. We added 10, so 0.0350 liters. So the concentration of the chlorine in this solution is 0.0285, and I'm going to leave this in my calculator, or chloride, I should say. But we have some amount of this solid, and some amount is going to be pushed back into solution, and that amount is going to be represented by an X. So I need to add X here, and then I can set up my KSP expression, because the KSP is going to be equal to the concentration of the silver times the concentration of the chlorine. And I know that my KSP value is 1.8 times 10 to the negative 10. The concentration of silver itself is X. And looking at this KSP value and my initial concentration, I can simplify this. So the concentration of the chlorine effectively is going to be 0.0285, and this value is just going to stick in my calculator. So then I can find this X, and the X is the concentration of the silver. I can find this X fairly easily by dividing my 1.8 times 10 to the negative 10 by 0.02857, whatever was in my calculator. And I actually get a nice even 6.3 times 10 to the negative 9. Now that represents the concentration of silver. So now I can fill that value into my master equation. My E cell equation is going to be 0.799 minus 0.05916 times the log of the reciprocal of the silver concentration minus the saturated calomel electrode, 0.241. And I get an E of the cell at 10 milliliters. In fact, I would probably have a chart up here. So volume of silver, E of the cell. So at 10 milliliters of silver, the E of the cell is 0.073. Yeah, that's a good amount of sig figs volts. So that's how you would calculate that here. Now let's calculate at the equivalence point. So at the equivalence point, we have taken all of our moles of silver, our point, let's see, that was 1.25 times 10 to the minus 3 moles of silver, and we have reacted with 1.25 times 10 to the negative 3. I hate it when you guys do that on quizzes, and here I went and did it, 25 times 10 to the negative 3 moles of our chloride, and we have formed 1.25 times 10 to the negative 3 moles of our solid silver chloride. So now the concentration of our silver, so this is at 50 milliliters of silver. So the concentration of our silver ion is going to be dependent on the equilibrium formed by the silver chloride dissociating into its ions. So remember, the solid has an activity of 1. We don't keep it in our Q value, but the concentration of our silver in our silver chloride is going to be equal to our molar solubility. So the KSP 1.8 times 10 to the negative 10 is going to be equal to x squared. Then x is going to be equal to the square root of that. So x is 1.3 times 10 to the negative fifth molar. And again, that is the concentration of our silver. So that is our pink value that we feed into our master equation. So the E of the cell is then going to be 799 minus 0.05916 times the log of the reciprocal minus the saturated calomel electrode. So at the equivalence point, so at 50 milliliters, I have an E of the cell. I have 2697. I would round that to 0.270 volts. So after the equivalence point, we're going to have an excess of silver, the way that this one is written out, because we're titrating with silver as the titrant. So after the equivalence point, that's 60 milliliters of silver nitrate, we have an excess of silver. So let's calculate those moles. Let's do it the long way. We had 1.25 times 10 to the minus 3 moles of our chloride. And with 60 milliliters of 0.025 molar, we have 1.5 times 10 to the negative 3 moles of silver. So we have an excess of silver. We need to subtract the moles of the chloride from the moles of the silver, and we have an excess of 2.5 times 10 to the negative 4 moles of silver. But that doesn't give me concentration yet. I need to take those moles and divide them by the total volume in liters. So the total volume, we had a 25 milliliter sample, we just added 60. So we have 85 milliliters, so 0.0850 liters for our total volume. So the concentration of silver at 60 milliliters is then 0.00294 molar. So that value goes into our master equation. And then the E cell is going to be equal to 799 minus 0.05916 log log, the reciprocal of my silver concentration, minus the anode, the saturated calomel electrode, 0.241. So at 60 milliliters of silver, I have an E of the cell of 0.408 volts.